For every pulsar that sends its radio beams towards us Earthlings, there must be a large number of these objects sending their rotating beams merrily into outer space. But there would be no way of our intercepting these beams. Pulsars come in a range of pulse periods and magnetic fields. Periods ranging from as slow as a couple of seconds to as fast as a little more than a millisecond. We can listen to modulated audio of the data from a few of these objects to get an idea of their rotation rate. Here we have one of the slow pulsars, a pulsar rotating once in about 0.7 seconds. This object, named Pulsar 0329 plus 54, occupies the portion of sky over here in the Perseus constellation. This was one of the earliest discovered pulsars. We can now hear the data from a much faster pulsar, one residing in a supernova remnant, the Vela. We then come to the fastest spinning pulsar known to us, rotating about 642 times in a second, so that the individual pulses seem indistinguishable in this modulated audio. Residing in this portion of the sky, in the constellation of Vulpecula. The numbers referred to in naming a pulsar pin its coordinates in the celestial sphere, something akin to latitude and longitude on Earth. Taking the Earth's equator and the meridian circle and projecting them onto the celestial sphere gives us a reference frame on the sky that can be used globally. Magnetic fields of pulsars vary from as low as 100 million Gauss, a typical unit of magnetic field strength, to as high as 100 trillion Gauss. It is only very recently that the highest magnetic field strength pulsars, called magnetars, have been discovered. Another interesting manifestation of pulsars could perhaps be, as some recently observed highly exotic objects, the gamma-ray bursters. Seemingly randomly located bursts of gamma rays observed from several regions of the sky. It is only in the recent years that it has been felt that these bursts of gamma rays are coming from sources which are, indeed, very far away, at cosmological distances. Very far away? This should mean that at origin, these gamma ray bursts must indeed be very powerful. These cosmologically distant objects seem to burst and vanish from our gamma ray site randomly. It is thought that perhaps these bursts arise from the merging together of two neutron stars spiraling towards each other. Coming back to ordinary pulsars, these are thought to be born spinning rapidly. How rapidly is yet controversial. We have been observing these objects, radio pulsars, for a few decades now. We have added years of understanding of stars, their birth, evolution and death, observations of historical supernovae, radio, optical, X-ray and gamma ray observations, and knowledge from many branches of physics to our accumulated wealth of studies of these objects. One rewarding meeting ground of these observations has been when we have observed radio pulsars in the hearts of the remnants of historical supernovae, the cosmic lighthouse progeny of historical guest stars